Alright guys, we're going to go ahead and talk about Johannes Kepler and the laws of planetary motion. So currently, with this activity, you're going to be working on understanding and using mathematical models to predict orbital patterns and events, which will eventually help you to master this standard right here, which is the solar system is comprised of various objects that orbit the sun and are classified based on their characteristics. And we're able to classify orbits based on their characteristics. So we'll start here. I'll go over here. Danish astronomer Tycho Brahe, 1546 to 1601, had an island observatory, and he was able to get the best measurements of all the positions for the planets as well as the moon through his observatory. He took on an assistant, an Austrian mathematician, Johannes Kepler, and he was interested in how the planets moved and went to Tycho's island in order to get more accurate measurements and really to assist and learn from Tycho Brahe. At the time, many astronomers believed that planets orbited around the sun in perfect circles. But Tycho's accurate measurements for Mars, and Mars was the big one that they could see because it's the brightest, it's the closest, didn't fit a circle. Instead, the mathematician Johannes Kepler found that the orbit of Mars fit an ellipse the best. So what is an ellipse? So basically they found that the sun is not necessarily in the middle of every single orbit. So most planets travel around the sun in this shape called an ellipse. And an ellipse is essentially an oval. An ellipse is a geometric shape and it has two foci. So if you remember looking back here, this only has one foci. If you've ever used a compass to draw a circle, you know you put one thing down and then you put the pencil down and it rolls around. An ellipse has two foci, so one here and one here. And one of these foci in this ellipse is the sun, and the other one is really nothing. And this is his first law of planetary motion, is that these planets were able to move around the sun and a foci that doesn't exist in the form of an ellipse. So planets don't move around the sun in a perfect circle. So a structure of an ellipse, it is structured like an oval, you'll see that. It has a major axis, which is this really long line across the fatter part of the ellipse, and a minor axis, which is the shorter portion. The perihelion is the side that is closest to the sun, and the aphelion, which is the side furthest from the sun. And the semi-major axis is just half of that long side. So the perihelion, when Mars or any other planet is closest to the sun, it's considered to be in its perihelion. When it is furthest away from the sun, Mars is considered to be at its aphelion. So Kepler also found out, I'm going to move all the way over here. Kepler also found out that Mars changed speed as it orbited around the sun. It was faster when it was closer to the sun, and it was slower when it was further away. But he discovered that the areas A and B, so the area in here in this triangle, swept out by the line from the sun to the triangle that Mars traveled in, was equal to the area that was swept out here in the same amount of time. And this is the second law of planetary motion. Kepler found a relationship between the time it took a planet to go completely around the sun, P, or period. It's the year of a planet, essentially, completely around the sun, and the average distance from the sun, or the semi-major axis. So remember, this is the sun, so the relationship between how long it took for the sun to go all the way around one period and how large the semi-major axis was. So essentially, if you doubled the semi-major axis, you'd be able to calculate how far across at the longest that the planet was traveling in its ellipse. And that is considered to be the third law of planetary motion. So basically, Earth's year, P, and distance, A, so P and the distance, this should be A right here. The average distance from the Earth to the Sun is A. It is called 1 astronomical unit. We talked about this last time. And so that to calculate, we can use the equation p squared, or period, the amount of time it takes to go around the circle, or around the ellipse, squared, equals A, this should be A again, or the half of the semi-major axis, or half of the major axis or the semi-major axis to the third. So by using this equation, Kepler is able to predict an unknown planet's period or year length or its distance from the sun at any given time. So Kepler's laws apply to really any body that's orbiting any other celestial body. So any planet that orbits the sun, how the moon orbits the earth, how satellites orbit around the earth, how the International Space Station orbits around the earth, or any rings that orbit around any given planet. They all function the same way. They all work the same way as far as calculating how far across they are, how long they would take to travel around something. So we could calculate how long it would take the moon to orbit the earth using this same equation. And Kepler was able to do that too. That's how we now know that it takes the moon 28 point something days to travel around the earth one time. And that's how we know that it takes every single, that's how we know the year length of every single planet, including our own, obviously. Later, Isaac Newton built upon Kepler's law to confirm his own law of gravitation. So basically, Kepler laid the building blocks of gravitation, of gravity. If it wasn't for Mars and its complicated travels across the night sky, Mr. Kepler would not have been able to derive his laws of planetary motion, and potentially Isaac Newton would not have been able to figure out gravity from that. And so the red planet Mars is forever linked to a great understanding of the solar system and one of the 4 basic forces of nature, one of the most important, which is gravity. So I hope you understood that. Write down any questions you have, and I will talk to you tomorrow.